We're very happy to have Albert Schwarz, because we're going to give us a talk that was a new approach to
Okay, thank you for inviting me. I would like to talk about some very general stuff first, and only after that I will go to string theory. So really, I was told that I should use minimal amount of information. I will do this. So what I will explain is how to start with one string space, once in BRST formalism. You can get amplitudes for interacting strings. At first sight, this is quite surprising, because interaction happens when you have several strings. But if you think deeper, you will see this is not quite surprising. The situation is can be explained from the fact that if you have two-dimensional conformal field theory, then every manifold, one-dimensional complex manifold or complex curve or two-dimensional surface, which has n+1 boundaries, specifies the map of nth tensor power of space of states to the space of states. So it's in the sense that you can get n-string space, n-string states inside one string space. But the fact is not very surprising, but still it is important. It is especially important for me because I invented all the stuff trying to express formally string theory in terms of algebraic approach to quantum field theory and to geometric approach to quantum field theory. And I should say a couple of words about these approaches. So basically, algebraic approach to string theory, starting point is the algebra of observables, which is associated to algebra with involution. So that's the most general approach that people know to quantum field theory, U. But there is a much more general approach that I invented several years ago, and I called it geometric approach, where the starting point is the set of states. And I proved that this approach is more general than algebraic approach, and, much more general. And, in the framework, this framework, you can really define scattering matrix, but not usual scattering matrix, but something that I call inclusive scattering matrix, which is related to inclusive cross sections. So in this approach, you can prove that you can get any theory from classical theory if you assume that only part of observables can be really observed. If our devices, if you assume that our devices can observe only a part of observables, then you can see that quantum mechanics and generalization of it are obtained from classical mechanics is restricted sets of observables. So that's so then I found that quantum electrodynamics can be really formulated very naturally in this approach. This is really important because in quantum electrodynamics, usual Fock space is not sufficient, and this explains what is called infrared divergences. Really, if you work with this inclusive cross-sections, then you do not have this infrared divergences. And so really, if you start with, if you do that work with Hilbert space and work with this more general approach, then this problem, infrared problem, mostly disappears. So that's, but this is not the stuff that I'm trying to explain today. The stuff that I will talk about today simply comes from the attempt to formulate string theory this way. And I did not succeed completely in this attempt. However, you will see that there are some interesting results that go beyond string theory. So, what will I do right now? I will consider not a string theory, but quantum theory that is obtained from quantization of classical theories, is first-class constraints, assuming that these constraints form a Lie algebra with respect to Poisson brackets. A string theory can be obtained this way, as well as superstring theory. And I show that in this case, you can consider standard physical quantities, but you can consider also a new kind of physical quantity. And these physical quantities, they, in string theory, they give what is called string amplitudes, scattering amplitudes of string states. So, but I start with this very general stuff. So, but first of all, I start with some mathematical observations that are really very well known. I mean, probably very well known to all of you, but probably in a little bit different language. And so the first thing is that if you have any manifold, you can construct a supermanifold, which is called pi Tm. This means that you take a tangent bundle to this manifold, and you reverse the parity of fibers in this tangent bundle Tm is the standard notation for tangent bundle. Pi is standard notation for parity reversion. That you even replaced by odd and odd replaced by even. So that if you have coordinates in M, and they are denoted by x1, xm, then, and if all of them are even coordinates, then you add odd coordinates that I denoted by xi1, xin. So, and really, there's something that you always do in differential geometry, where you add to coordinates also differentials anti-commute. So, polynomial functions on pi Tm should be identified with differential forms on M, but you have not only, if you have finite dimensional manifold, which is usual given coordinates, then you have only the finite number of odd variables, and so all functions are polynomial. So all functions on pi Tm, in this case, are polynomial functions of odd variables. However, you can consider the case when your manifold M is a supermanifold. Then still you can define pi Tm, changing parity of axes. And then you have polynomial functions, but also you have functions of different kind. And these more general functions are called pseudo-differential forms on M. But still you can define a differential by standard formula. The Ram differential denoted usually by D, but I use the notation Q because in physics, this Q is almost always is this BRST operator. But in any case, and commutation by Q with itself, or Q squared, is equal to 0. And so you can say that Q is an odd vector field satisfying this relation. And it is called homological vector field because having such an operator, you can define homology. You can consider Q closed elements which are annihilated by Q, kernel of Q. They are cycles or co-cycles, depending on terminology. And there is an image of Q. These are Q exact forms that are, in mathematics are related to boundaries or co-boundaries. But I hope that this is very well known, maybe different, the odds are different. But what is interesting, this is, sorry, that you can integrate pseudo-differential forms. So this basically this is the same Bayesian integration. It's, we are familiar in super mathematics. So you can always have considered the integral, but this integral is not always.
So what is the crab?
So?
What's the
sorry, I think that I skipped one of this. I don't know what happens. Sorry. Okay. So what is I did not introduce this notation, and prime is another notation for pi t n. I will also use it. And so that's so if you can integrate for if you have a pseudo differential form of n, then you have pi t of n, which is n prime, is a part of pi t n of pi t n, and this allows you to integrate pseudo differential forms, to restrict them to submanifold and integrate over submanifold. So
I also don't understand what do you mean by pseudo?
By what?
Pseudo differential form.
Pseudo differential forms is by definition a function on pi t.
It's a family variable.
So really, this you have. So what is differential form? Differential form is a function of x and psi. Yeah. But when we talk about differential form, you consider polynomial function of psi.
That's right.
If you have a function which is not polynomial, and this can happen if your x's are not necessarily even, if they are odd, then xi's can be even. And therefore, you can consider something like exponent of minus xi squared.
Okay.
And this is pseudo differential form, but it's not a differential form. It still can be integrated. So therefore, you should remember that this is notion of pseudo differential form is really the main notion that you should have in when you consider when you start with supermanifold. So, sorry. So now what I can say that this pi tn has a very nice invariant interpretation. Right? So I defined it in terms of coordinates, but you can define it in an abstract way. This is space of maps of 0, 1 dimensional superspace R01 into M. No, of course, this is more or less by definition. But this interpretation is very natural. Or mathematical say that this is functorial. It is really can be is this an agreement with maps? So, but then the next thing that I would like to say, that in this interpretation, this Dirac differential has a very interesting, very simple description, because really, look, you have a maps of R01 to M, but on 01 you have vector fields. Not too many of them, you have one even vector field and one odd vector field. But every vector field on R01 generates a vector field on the space of maps. And odd vector field generates precisely this differential. And even vector field, it generates really what is called grading, or physicists say Gauss number. So from this interpretation of pi TM, you can say that if you started with Lie algebra called G, then pi TG will be a super Lie algebra. And more or less, you will have a differential there. This q square is equal to 0. And this differential I will denote by q. Sometimes really it is convenient to consider even larger the algebra, include this q, the differential as element of the algebra. This simply another language, but sometimes it will be convenient. And if I include the differential, you can, I will denote this by this pi tg is denoted by g prime. And if I also include the differential, it is denoted by g is 2 primes. You also can include Gauss number, but this will be more or less irrelevant for me. So, and this is the construction that probably you have seen. So really look, let us suppose that you have a Lie algebra with some generators T, and you have some commutation relations. That F are structure constants. Then you can consider a new super Lie algebra, adding some odd generators B with commutation relations that are written in this slide. So this is something, this relation that appear more or less very, very often in physics. Usually keys, they appear in topological quantum field theory, where keys will be energy momentum, and P is Gauss, and energy momentum is in topological quantum theory is Q exact. It is acting by Q on P, you get T. So you have this relation. This is standard stuff in physics. But, this is, as I explained, this is a very natural construction in mathematics. So the terminology is as follows: that if you have this relation that I have written here, this the algebra is G prime, and you add Q to this Lie algebra, this is G2 primes. So, but also, you can consider this for groups. If G is a supergroup, curly G is a supergroup, then G prime, which is pi Tg, is also a supergroup because, as I explained, the elements of G prime, points of G prime, are simply maps from R01 to G. You can multiply these maps and you will get a new supergroup. And the Lie algebra of the supergroup is precisely this G prime, where G now is the Lie algebra. So this basically, this is the construction, the same construction that appears in physics all the time, can be exponentiated, can be integrated, you would like, from the Lie algebra to the group. Okay. Now, until now, this was simply something that is a collection of mathematical definitions that you definitely know in many particular cases. But now let me go to physics. Let me consider a classical system where let's assume that after quantization of this classical system, you get quantum system with some Hilbert space denoted by curly E. Now you can get new classical systems imposing some constraints on your phase space. And you know that if you have a constrained system, then it is very convenient to use BRST formalism. And this BRST formalism means that instead of constraints, you add ghosts. So that's the picture is as follows. That you can take a new space, which is denoted by E prime here. And this is a tensor product of E with some representation space of canonical anti-commutation relations. These are, of course, denoted by C and B. Then you can say that these constraints generate some operators T, Tk by the act on this Hilbert space, and you want to introduce the relation Tk is equal to 0, but you cannot. You know, this is the wrong way to do this. There are many ways to avoid problems in this setting. And one of the problems, one of the solutions is to introduce ghosts. And then you get BRST operator in E prime, which is written with the formula here. And mathematicians say this Q is this is differential in the complex that calculates the cohomology of the algebra. But for me this terminology is irrelevant. So anyway, you introduce the C prime, this BRST operator, and you introduce improved TK, adding this stuff, structure constant by C by B. This is will be BRST trivial stuff. Okay. And then you work in this BRST formalism in standard way. Physical states are Q exact, Q physical states are Q closed, they're on the kernel of Q. The image of Q gives you BRST trivial states that you can neglect. And that's stuff that is very well known to you. You know also that the relation Q square is equal to 0 is that it's true when you are working with finite number of degrees of freedom. But if you have infinite number of degrees of freedom, then you have problems. You should you can have anomalies. Q square is not equal to 0. For string, Q square is equal to 0 only for critical string. You know that if you have many infinite number of degrees of freedom, then the representation space, the representation of canonical anti-commutation relation is unique. You should choose one. But this is the standard stuff that I do not want to talk about. So until now, everything was very, very standard, maybe except notations. But now, what I would like to say, that if you have a representation of Lie algebra, then you can hope that this representation of Lie algebra is obtained from a representation of some Lie group. This not always happens. This always happens, almost always happens in finite dimensional case, but in infinite dimensional case you have problems. But still, if you cannot integrate the representation of the algebra to the representation of a group, you usually can integrate it to a representation of semi-group. This will be important for me, but at this moment I simply assume that I can integrate this, my representation of the algebra, which means that there is a representation, capital psi, of the group G prime. Psi was a representation of Lie algebra, G prime, and here G, but here G is curly G. And so let's assume that my representation psi can be obtained from a representation of the group. Now, what does it mean, a representation of the group? This means that for every element of the group, you have an operator. So you have a linear operator. So, and you can go back. If you have a linear function on the space of linear operators, you get a function on the group. But remember, your group is G prime. G prime is pi t G. A function on operators goes, linear functional operators, goes to pseudo-differential form of the function on G prime. And this is pseudo-differential form on G. And you have BRST operators everywhere. You have, in mathematical terms, you have differentials. And so this means that if I'm saying that my map agrees with differentials, and this means if you take a Q-closed element on L star, then you will get a Q-closed function on G prime, or if you will have a closed pseudo-differential form on G that you can integrate and to get a number. And this is the main idea, how to get new numbers from this construction, this setting that is very standard in physics. So I will consider a particular case of this construction. But I will explain this on the next slide. But now I would like to say the following. So yes, what did I do? I have a map of this G prime to something. I get a closed pseudo-differential form on G, and I can integrate it. The problem is that this construction usually doesn't give anything interesting. However, there is a trick which is as follows. I will show that sometimes this function on G prime descends to the function of G prime factorized with respect to something. And then the statement is then you again get a pseudo-differential form that you can integrate. And this time you will get a lot of new interesting numbers, in particular string amplitudes. So that's
I didn't quite get it. Just repeat the last.
Sorry.
Just repeat the statement. I did not understand what you had said. Just your last sentence. I didn't understand.
Let me go to the next slide.
Okay.
And then I
Sounds
think
good.
that probably will disappear.
Very good.
So this is the next slide. First of all, before to go to really to the next slide, something really important, but completely formal. So here, what did I do? I factorized a group with respect to a subgroup. And that's not something that appears in real situations. Usually, when you are working in infinite dimensional setting, then subgroup, if you have a Lie subalgebra, then then not necessarily you have a corresponding subgroup. And so therefore, instead of subgroups, I will consider Lie subalgebras of Lie algebra of my group. So, and this is what the content of this slide is the statement. You also can work with Lie subalgebras instead of Lie subgroups. But I do not want to to draw attention to this technical stuff. You always can think about subgroup instead of subalgebra, but in reality, you should work with subalgebras. So now, so let me, I will skip some slide. And now what I will think I will answer your question. What I will do, look, I have the space L, which is the space of operators in my Hilbert space of linear operators. This is L. Of course, in this space of linear operators, I have in my Hilbert space, I have BRST operator. In the space of linear operators, I also have BRST, which is simply commutator with Q. So that's so I can consider everything which is closed, everything which is Q closed, Q exact, and so on. Now, what I'm doing, I'm considering an element rho from my space E prime, where in E prime I have BRST operator called Q, and I assume that I take this state rho, which is Q closed, which is annihilated by Q. Also, I will take in dual space also a Q closed element, which is denoted by chi. And now, on the space of linear operators, I write this formula: sigma A, which is inner product chi, then A, then rho. Matrix elements of A between chi and rho. This is sigma A is element of L star, of something that is dual to space of operators. And what I'm saying, this element is also BRST closed. Yeah, you have you have this function sigma of A is also BRST closed. So, but then what I'm having, I have a map from G prime, purely G prime, to space of operators. You have representation. What is the representation of G prime? This is a map in the space of operators. And then I write the formula, which is written here. Psi star of sigma applied to G prime is simply given by this formula, chi psi G prime rho. So basically what I am doing, I have, what is the idea? I do not work with Lie algebras. I work with Lie groups or semi-groups. Then I have a map. In physics, you consider the map representation of Lie algebra, which is a map of Lie algebra to something. Here I integrated it to the map of a group or semi-group. And then this map it agrees with differential, and therefore it gives me a possibility to transfer something that I constructed from the very beginning, which is Q closed in the space L. I get something that is Q closed, which is BRST closed on G prime. But this is a pseudo-differential guy, pseudo-differential form that I can integrate, and I can get a number. But this, as I said, this is not sufficient, because I do not get enough interesting numbers. But I will get interesting numbers if I can factorize my G with respect to something to get an non-trivial topology. And that gives me new physical quantities. And one of them is string amplitude. Did I answer your question?
I think so. And what will be the other interesting quantities? What other interesting? You say string amplitudes will be one of them. Does it give you just string amplitudes or something else also?
So at this moment, I know how to construct string amplitude. I have some conjecture that maybe how to construct non-perturbative string amplitude this way. But I believe that this is a very, very general construction. It could work in any case. This is so, and now I should really go ahead and explain the conditions. They are very simple conditions that allow me to say.
Actually, I still don't understand. So you're saying that when people constructed the BRST formalism, when people constructed the BRST formalism for string theory, that they missed the fact that you can extend this to get scattering amplitudes as well? What did they miss specifically? Like, nobody thought of this, or they missed something technical?
I didn't hear the question. What? Say it again.
So I'm trying to understand what is the new thing here. Did people miss some technical aspect in BRST quantization? Or they didn't think of this in the right way, or what?
So
why hasn't this been done 40 years ago?
The statement is this as follows. It is non-trivial statement that if you have one string state, usually people think that one string state, there are n string states, and so that's and you have a n string state, you have interaction, and the interaction gives you amplitude.
Right.
But what is surprising, I try to explain this, it's not very surprising, but still it is surprising, that if you have one string space, this means that you don't have any interaction. Right. You have only BRST operator.
So this gives you some
without any interaction, you can get string amplitude.
So this gives you a natural way of constructing vertex operators. Is that the point?
I do not want to talk. I don't consider precisely what the word vertex operator doesn't appear here, but you will see that it is something. Okay. It is hidden, but I can explain where it is hidden, but it is hidden.
But are you okay? And this guarantees you're guaranteed that you get all scattering amplitudes, or just
all perturbative string.
Yeah. Great.
Yeah. Okay. Yeah. So the statement is that I give very simple conditions to say that you can really, your form that you get, this closed form, it descends to G over K, where K could be a subgroup or Lie subalgebra. And so what is written in this slide, it is an absolutely trivial formal calculation that gives you these proofs for the case when you are working with subgroups. A little bit more subtle calculation gives the same result for Lie subalgebras. But this is it's very simple proof, but the result is as follows. So that's you have something that the form that descends to the quotient. And but there is a requirement here that this rho should be invariant with respect to this stuff. So the requirement is, so look, you have subalgebra K, there is corresponding stuff that is denoted by K prime, this is by TK, and the requirement is that rho, this is one of the guys that I included in my formula for sigma. This rho should be invariant with respect to K. But and this is simple calculation shows that you have the in this case you will have this ability to say that your pseudo differential form descends to the quotient. You can integrate the quotient with it and get new numbers. But rho and chi are.
So earlier you said that if you just work with G or the curly G or small g or whatever, that you get trivial invariance, and it's crucial to work
With quotient.
with the
Yeah.
quotient. What's in string theory context? What's this h? What's h going to be? The little
What?
h, the subalgebra h. What's it going to be?
So I will answer this question. Really, you're asking how to find this rho.
Yes,
This
that's
is,
right.
yeah, this
Okay.
will be. I
Okay,
will
good.
answer this. Yeah. But the situation here is for chi is more or less the same. You can formulate precisely the same statement. You should impose some conditions of invariance on chi. I wanted to impose condition of invariance with respect to some subgroup. And so then what you have here, you can you will have the statement that the quotient excuse me, my pseudo differential form, it will descend to the double cosets. So really, you have rho from the right, chi from the left, and basically you can factorize with respect from the right with respect to the left. So this basically you will have something that gives you a function on the space of double cosets when you wrote primes, or you will have pseudo differential forms on double cosets when you do not write primes. This is simply a question of terminology. Yeah. The next remark is that this construction can be also repeated in the case when you're working with not with the spaces by itself, but with the tensor powers. So that's the same as I will need this. But now I would like to apply this stuff to string theory. So first of all, you can do this in two ways. The first way is to say that string theory can be obtained by this construction when you imposing constraints, you simply repeating all the stuff that I said in concrete situation. But it's not quite necessary because basically what do you have? You have, when you have one string space, this is space that you are always working with, yeah. Then in this, for bosonic string, what do you have for bosonic string? You have Virasoro operators, if this string is closed, you have a pair of Virasoro operators, ln and tilde n. And these operators are Q exact, because you have, of course, Ln is the anti-commutator of BRST operator, this Bn, and this is precisely what what is called G prime in my notations. So basically, what do we have for without any classical consideration in bosonic string, you have a Lie algebra denoted by diff this Lie algebra of complex vector fields on a circle, and you have a representation of this Lie algebra, and moreover I have a representation, really two representation of this Lie algebra, ln L tilde n, and you have this Bn and B tilde n that give you representation of diff prime, and you have BRST operator which gives you a representation of diff 2 primes, basically two copies of diff 2 primes. Basically, without any classical considerations, you get this stuff from for string theory in space. But also the same picture, more or less the same picture appears for superstring. The only difference is that you should consider supersymmetric generalization of this algebra of vector fields on a circle. But what is one thing that is important to notice, that really when you consider scattering, you should not work with all elements of this Hilbert space. You should consider impose the additional conditions that is written here, and these additional conditions mean that you have an action of a circle, U1, if you would like, which is denoted here by S1, and these conditions can be treated as S1 prime invariants. So this is something that you should consider when you take something when you consider scattering. You should impose these conditions. Now, now we would like to basically what we would like to do. We would like to apply our main construction. Main construction, this it requires chi and rho, and rho should be invariant with respect to something. Chi should be invariant with respect to something, and then you will get something that I want to have. So I should find what what should what are appropriate chi and rho to get string amplitudes. But basically, I would like to work with this nth power of my space. Then you have the algebra, direct sum of some copies of the algebra G, which is the algebra of vector fields for the case of bosonic string. And so I would like to find this some subalgebra of this direct sum of the algebra of vector fields. The very natural way to construct this such a subalgebra is as follows. You simply take n circles. Remember that your G's consist of vector fields of complex vector fields on a circle. You should take n circles. You should embed it in some complex manifold. And you should consider complex vector fields on the circles that can be extended to holomorphic vector fields somewhere. So this is a very natural construction. In particular, the simplest possibility, you take a complex manifold M, you will take a one-dimensional complex manifold with a curved surface of genus G with some boundary components, with n boundary components. And then you consider vector fields on the boundary, but not all of them, but only vector fields that can be extended holomorphically to the interior. And this will be a very natural Lie subalgebra. And this is precisely the subalgebra that appears in bosonic, in string amplitudes for bosonic string. Something very, very similar appears in superstring. So also you should look at this chi, and so for chi is again in the nth power of your Hilbert space, and you would like to have this related to scattering. The natural condition for chi is invariance with respect to S1 to the n copies of S1, and everything is prime. You should. This is precisely means that your chi is a product of chi1, chi-n, and every is chi y has a chance to represent the particle. So, and the statement is that this construction is this choice of k and this choice of u. This construction gives precisely string amplitudes. And let me explain why this is so. I will not prove this, but I will explain how to get this stuff here. Look, what happens in standard approach? In standard approach, and that's already
So for chi, you just take a state in the n-fold tensor product of one-dimensional Hilbert spaces, and U is you ask that it's invariant under BRST orthogonals.
Yeah.
And for psi, you say what? That is
so this is an Lie algebra of fields that have holomorphic extension to the interior of.
So it's also a state in the nth tensor product, but the gauge group is just whatever you can extend holomorphically inside a fixed genus G surface with n boundaries.
Yeah, and then I should go to standard stuff. Standard stuff. I'm using what is called operator formalism of string theory, and is very closely related to the Siegel definition of conformal field theory. And I am not sure that I hope that this is well known. But, still, I would like to. I don't want to assume this. So, what standard notation curly Pn is the moduli space of one-dimensional complex curves with boundaries consisting of n-parametrized circles. Or this is the same. You can say that these are complex curves with n embedded parametrized disks. And then this you can paste together curves of this kind. So in particular, you can consider space which is consists of annuli. Annuli is annulus is in my notations P20. We take a sphere, genus 0 surface, a sphere, and two disks, two boundaries. You get an annulus. So A is the moduli space for annuli. And this A can be considered a semigroup. You can paste together two annuli, get new annulus. Or you can paste this annulus to any boundary. You will get an action. You say that this curly A is a semigroup which acts on curly Pn. This action is transitive. You can understand it. It's a transitive action of semigroup on pi n, And then you can say that if you take a stabilizer of this action, Lie stabilizer, this means that elements of Lie algebra, by the way, Lie algebra of A, of this semi-group, is precisely this algebra called TIF, the algebra of vector fields. And so that the stabilizer is precisely this subalgebra that I explained. And yes, you can say that this Pn is A to the n factorized with respect to this stabilizer. And then the next thing to say is that the group S1 to the n acts on curly Pn. And this is again a very well known thing, simply rotate these boundaries. So the quotient space stands, the standard notation of it is Pn hat. And so in usual calculation of amplitudes, you take a such cycle in Pn hat and integrate, and you will get string amplitudes. And the statement is that this standard construction is precisely the same construction that I considered. So basically, you will see that A to the n, if you take double cosets from the right, you take this stabilizer, from the left you take S1 to the n, and you will get precisely this Pn hat. So this allows me to identify these two things. So now what I would like to do, I would like to go to supersymmetric fields, to superstring. And basically, the statement is that for superstring, everything is also very natural. It's more or less the same. What happens here? Let me explain. Let's say we'll consider together bosonic case and case of superstring. And this goes as follows. First of all, you can define a notion of standard conformal disk. This simply module C less than 1 on complex plane. Then you can define a notion of standard Navier-Schwarz disk. You have also standard disk and odd variable theta. And you have odd vector field, which is standard covariant derivative, which is written here. And you have standard Ramon disk. It consists of the same points, but you have another odd vector field, which is singular at 0, but non-singular everywhere else. So and you can define conformal manifold spaced together from standard disks, and superconformal manifold is spaced together from Schwarz disks and Ramon disks. But by means of transformation, it should have odd holomorphic vector field D, which is defined up to multiplication by non-vanishing holomorphic function. And you have superconformal manifolds spaced together from NS disks and R disks. Then what you can do, you can calculate, take symmetry groups of, can define in natural way superconformal annuli, and you have again maybe Schwarz annuli and Ramon annuli, and you can consider standard NS and R annuli, which is simply defined by means of relation that modulus of C is between A and 1. So this annuli can be interpreted as strips, as usual annuls can be interpreted as a strip. This guys also can be interpreted as strips. And this allows you to find easily symmetry groups of standard annuli. So that they are described on this slide, the next slide. And so basically, what do we have? You have rotations for NS annulus. You have rotations and odd symmetry for Ramon annulus. And also in both cases, you have discrete symmetry, which is reflection of odd variable in strip picture. And now, again, you can define an analog of PM. Curly PM was defined as curves, these M-embedded standard disks. But here you can define modular space PMN when you have superconformal manifold with M-embedded Ramon disks, M-embedded Schwarz disks, and N-embedded Ramon disks. So again, you have some analog of semi-group A. You have really two analogs, one for Schwarz, one for Ramon. You can consider corresponding Lie algebras. They are standard superconformal superconformal Lie algebras. When you have these operators Again, there are Sora operators and odd operators, Chen, and so on. These are standard stuff that I would like to skip. So you see that the standard, I wrote here the standard commutation relations of these algebras. But then you can consider scattering amplitudes. And again, what do you have? Here you have the condition for particles, for scattering states. And these are this condition is invariance with respect to the symmetry group equipped with primes. So this is this contains standard conditions that you impose in superstring. The invariance with respect to discrete symmetry. It is what is called GSO projection. So and basically what do you have? You consider this space curly A, these indices M and N. So you have there, remember that this K was defined as least stabilizer of X corresponding Lie algebra. Here you have also the same definition. The algebra is different, space is different, but the definition is the same, it's least stabilizer. And so that's but from the right hand side, when you have chi, you have the condition of this U, this group U that I have taken. It is induced by symmetries of annuli. And again, you get here the same stuff that we had for bosonic string. We had a definition of string amplitudes in terms of one string space of superstring. And really, I was not very, clear here what happens here. Because I considered really one group, one Lie algebra diff, one analog of it. But really, this means that I basically considered the situation when I have left-right symmetric theory. If you have heterotic string or superstring of type 2b, then you should apply separately this consideration to left sector, left sector and right sector. But basically the considerations are the same. So this is more or less the end of my story. The only addition to this stuff is that basically what did I do here? I worked in operator formalism. I didn't describe very precise way what does it mean. But what I would like to say that I could explain what does it mean operator formalism in a very simple way. In the cases when I need really when we are working with string, bosonic string or superstring, you need superconformal series that are described by quadratic action function or quadratic Hamiltonian. And in this case, operator formalism can be described very easily, but I do not have time to do this. So this is the end of my talk.
Any questions?
So, do you have any?
I mean, as you said, this is equivalent to the formalism we had already had.